Okay, so this morning, which is obscenely early, 5:30 on a Saturday morning, I'm wide awake and the gym's not open, so I thought I'd get another video done. And I'm doing the last lecture that's for the in-class test, and this is where chapter 12 starts to get a bit harder, but this shouldn't be horrible. None of it should be horrible, but the stuff in 12, 7, 8, 9, and 10 is challenging enough that I didn't think I'd want to put it on an in-class test. So this is a homework assignment. This is a video assignment. There aren't any odd problems I need to do in the video because every odd problem has a brother even problem that matches up perfectly with them. So as you're going through the homework, if you get stuck, if you try to do problem 17, I'd suspect problem 18 has the same sort of skill. If you try to do problem 49, I'd guess either 48 or 50 would have the same skill. You should be able to kind of tell where a problem, if you're having difficulty with, where kind of it has a helper on the video. So this is another section on probability, and the first few problems that I picked, 14 and 16, require using a formula, and I'm going to go slightly backwards when I'm lecturing. I'm going to do problems 18 and 20 first and use those to explain the formula that the author has given me, and then I'll go on and do the rest of the section. So let me just get started here. So the nice thing about a few of the problems in this section is they can be done with the skills that we already have. And that's the case for problems 18 and 20. So in section 12.6, problems 17 through 20, of which 18 and 20 sit in, it says a single dice is rolled. Find the probability of. And we've already done this. I'm pretty sure. We did double dice anyways, which is harder. So for what it's worth, the sample space in rolling a single dice, you could roll the numbers any number between 1 through 6. I'm not rolling 2 dice, so I don't need to make a tree for the sample space. Those are all the things that can happen when I roll a single dice. I can roll any number between 1 and 6. And 18 ask me what's the probability that I roll an odd number or a number greater than 2. So or means it could satisfy the first criteria, the second criteria, or it could satisfy both criteria. My probability is going to have a denominator of 6 because there's 6 things that can happen. And I'm going to circle all the elements of the sample space that are an odd number, or they're greater than 2, or they're both an odd number and greater than 2. So 1 is an odd number, so it satisfies that. Well, actually 1, 3, and 5 satisfy that they're odd numbers, so they would be some events that could go for counting in the numerator. And for the numbers greater than 2, 3 is greater than 2, 4 is greater than 2, 5 is greater than 2, and 6 is greater than 2. So I've circled or squared 5 different numbers. The probability that I get either an odd number or a number greater than 2 is 5 and 6. What our author would have wanted me to do for this is not solve the problem this way. Our author would have wanted me to solve this problem using the formula that he presented in problems 13 through 16. And so I'm going to get the same answer doing the formula approach that the author would want me to do. The formula approach is way more complicated for this particular problem, and I wouldn't use it. But to do the formula approach, I need to call the events letter. So I'm going to say A is the event of rolling an odd number. I'm going to say B is the event of rolling a number greater than 2. I'm going to say A and B is the event of rolling a number that's both odd and greater than 2. And A or B is the event of rolling an odd number or a number greater than 2. So this is overkill in terms of work. What I did to solve the probability, just understanding what's acceptable, finding all the acceptable numbers, putting the number of those in the numerator, and the 6 choices in the denominator is the way that I would attack this problem, but it wouldn't help you understand the formula. So now I'm going to resolve the problem using a formula the author gives me. The formula that the author gives me, the author says this formula is true, that the probability, P means probability, of the event A or B equals to the probability of the event A plus the probability of the event B less the probability of the event A and B. It is way more complicated than what I've just done. So I labeled some events. I labeled the event A as rolling an odd number. The probability of A is the probability of rolling an odd number, and the odd numbers are 1, 3, and 5. So the event A that I made up, which is one of the 2 things the author said was okay, has a probability of 3 and 6. The event of rolling a number greater than 2 would be rolling the numbers 3, 4, 5, or 6, and the probability, I put a P in a parentheses to mean the probability of the event B, would be 4 and 6. A and B, the probability of events A and B is the probability of rolling a number that's both odd and greater than 2, and the numbers that are both odd and greater than 2 are 3 and 5. So the probability of rolling a number that is both simultaneously odd and, I should have really written the word and here, greater than 2, is going to be 2 and 6. If I take these 3 things and plug them into the formula, it says the probability of A or B, which is the event of rolling an odd number or a number greater than 2, which is what I wanted to compute for this problem, is going to be 3 and 6, which is the probability of A, plus 4 and 6, which is the probability of B, minus 2 and 6, which is the probability of A and B. If I do this addition, or combine these fractions together, because they all have the same denominator, I simplify the fraction by just combining the numerators. 3 plus 4 is 7, minus 2 is 5. And this says the probability of rolling an odd number or a number greater than 2 is 5 and 6. So I can get the exact same answer using the formula for this problem as opposed to just understanding what the problem's asking of me and doing the probability like I'm used to. I'm going to do problem 20 just like this, and then I'm going to go backwards and do problem 14 and 16. And problems 14 and 16 require me to use this formula. And this formula, if you get a little bit higher and study more probability, it comes up frequently, so it's kind of worth being exposed to. But it isn't like something that's super important for our purposes, but it does come up in higher probability problems. So problem 20, same thing, I'm rolling a single dice, asks me what's the probability that I roll a number that's either greater than 3 less than 5. I know my probability is going to have a 6 in the denominator because the only numbers that I could roll are 1, 2, 3, 4, 5, or 6. The number of things that I put in the numerator are anything that's either greater than 3, less than 5, or both greater than 3 and less than 5. So for the greater than 3, the numbers 4, 5, and 6 satisfy the greater than 3, so they would need to be counted in my numerator. For the less than 5, I get the number 4, 3, 2, and 1. So I have circled all the numbers that are less than 5 and squared all the numbers that are greater than 3. Any one of those numbers, if they came up, they would be considered a success, that I've either rolled a number greater than 3, less than 5, or both greater than 3 and less than 5. So the numerator for this particular answer should be 6. There's a 100% chance of rolling a number that's either greater than 3 or less than 5. There's no number that I can roll that is both greater than 3 and less than 5. Our author would want us to do the problem like this. Our author, so I'm done. I'll get the same answer. The author wants us to do this with a formula. The author would say, let A be the event of rolling a number greater than 3. And then so the probability of A, the numbers that are greater than 3 are 4, 5, and 6. So the probability of A, there are 3 numbers of the 6 that I could roll that satisfy A. I'll make B the event of rolling a number less than 5, and the numbers that I could roll that are less than 5 are 1, 2, 3, and 4. So the probability of B is going to be the 4 numbers that satisfy B out of the 6 numbers possible. A and B is going to be the event of rolling a number that's both greater than 3 and less than 5. And 4 is the only number that's simultaneously greater than 3 and less than 5, because 4 is greater than 3, it's less than 5. Any other number like 5 isn't less than 5, 6 isn't less than 5, and 3, 2, and 1 aren't greater than 3. So for the probability of A and B, it's going to be 1 in 6. What we've actually found is we found the probability of A or B, because the probability of A or B is the probability of rolling a number greater than 3 or rolling a number less than 5. So that's what the author wanted me to compute in terms of my A and B is the probability of A or B, and I could use the formula. The probability of A or B equals the probability of A plus the probability of B plus the probability of A and B. I'm trying to compute the probability of A or B. I figured out the probability of A was 3 in 6. The probability of B is 4 in 6. The probability of A and B is 1 in 6. If I simplify these, I get 3 plus 4 minus 1 over 6. And that comes out to the same 6 and 6 that I already knew. So there are lots of formulas that are taught in classes that do more probability than we do. This is a common formula. In general, I don't use formulas unless they're kind of forced upon me. If I could answer probability questions, kind of not using formulas, that's probably a better way for me to understand the problem. And in both problems 18 and 20, the problems were simple enough. The sample space wasn't that complicated. I could understand the questions. Using this strategy, forcing the problem into a formula doesn't really feel like it's the best thing to do. But there are times that these formulas are useful. I go backwards and do problems 14 and 16, I can't solve those without the formula. So I just did 18 and 20. 18 and 20 should work just like problems 17 and 19. Now I'm going to do problems 14 and 16, which should work just like 13 and 15. And problems 13, 14, 15, and 16, they all want me to just get used to using this formula. And it almost gets to the point where we're doing algebra here, but it's barely algebra. So for problems 13 through 16, I'm using the formula, the probability of A or B equals the probability of A plus the probability of B less the probability of A and B. What the author gives me is 3 of these 4 values and wants me to find the missing value. In problem 14, the author says if the probability of A or B equals 0.9 and the probability of A equals 0.5, the probability of B equals 0.6, the author says find the probability of A and B. To do this question, you absolutely have to have this formula. I'm just going to plug the numbers in place of the symbols. So for the probability of A or B, I'm going to replace that with the number 0.9. For the probability of A, I'm going to replace it with the number 0.5. With the probability of B, I'm going to replace it with the number 0.6. And I'm going to leave the probability of A and B alone. So I just want to solve this now for the probability of A and B. I'm going to add those 2 numbers on the left side. So I'm going to go 0.5 plus 0.6, and I subtracted 0.5 plus 0.6, and I get 1.1. So the algebra, if I bring it down here a little bit, I get 0.9 equals 1.1 minus the probability of A and B. I'm going to minus 1.1 from both sides. On the left side, that subtraction I don't care to do without a calculator, so I'm going to go 0.9 minus 1.1, and I'll get negative 0.2. Our author might write negative 0.2. On the right side, I just have the negative sign and the probability of A and B. All probabilities have to be between 0 and 1. To get this probability of A and B solved for, I'm going to divide both sides by a negative 1. On the left side, the 2 negatives will cancel, I'll get a positive 0.2. On the right side, these 2 negatives will cancel, and I'll get the probability of A and B. So the author asked me to find the probability of A and B, and I can say the probability of A and B happening simultaneously is 20% or 0.2. 16 is going to work basically the same way. The author is going to give me values for 3 of the 4 pieces of the formula. I'm going to replace the pieces with the numbers, and I'm going to solve for what the author asked me to solve for. So in problem 16, the author wants me to find the probability of A. So if I'm doing problem 16, I'm going to use the formula to get my answer once I know what the unknowns are. The author gives me, says if the probability of A or B equals 0.6 and the probability of B equals 0.3 and the probability of A and B equals 0.1, the author says find the probability of A. So I'm going to use the formula, the probability of A or B equals the probability of A plus the probability of B less the probability of A and B. Now plug the numbers into the formula. For the probability of A or B, I'm putting 0.6. I'm bringing down my equal sign. I'm trying to find the probability of A. I'm going to leave that symbol in the problem. For the probability of B, I'm going to change that to the number 0.3. And for the probability of A and B, I'm going to change that to 0.1. I'm going to simplify the numbers on the right-hand side of the equal sign. So I'm going to go 0.3 minus 0.1, and I get 0.2 or 0.2 if I want to. So simplifying the right-hand side, I get 0.6 equals the probability of A plus 0.2. I'm going to do a little bit of algebra. I'm going to subtract 0.2 from both sides, or 0.2 if I don't write the 0 to the left of the decimal. I'll just do the math on the left-hand side. So I go 0.6 minus 0.2, and I get 0.4 or 0.4. I don't need the 0 to the left of the decimal place, but it's okay to have it. On the right side, I subtracted this 0.2. The 0.2's cancel, and I get the probability of A. That's the answer the author's going to want for problem 16. So each of the problems, 13, 14, 15, and 16, I can solve the problems by just shoving the numbers into the formula. Problems 18 and 20, and your homework problems 17 and 19, you can force the problems into the formula if you want to, but you don't have to. You can do the probability of rolling one dice with just doing traditional probabilities, just counting the number of things that are acceptable out of the number of possible outcomes. The next problems, 22, 24, and 26, the author hopes for me to use the formula to solve those problems. I'm not going to use the formula, but I might show you once or twice how to use the formula. These will match up perfectly with your 21, 23, and 25. Those are kind of the same problems. So 21 through 26 all are card problems, and it's picking one card from a deck of cards, and the author wants me to compute some probabilities. And these problems are maybe more formula worthy than the others, but I don't really think they are that formula worthy. But you could do them with a formula. So 21 through 26, the author says one card is selected from a deck of cards. Find the probability that each of these probability questions is going to have a 52 in the denominator, because there's 52 different cards I can pick from if I'm picking one card. 24 says, what's the probability that I pick an ace or a 2? The numerator needs to be any card that's either an ace or a 2. So that would be the ace of diamonds, the ace of hearts, the ace of clubs, the ace of spades, and then the 2 of diamonds, the 2 of hearts, the 2 of clubs, and the 2 of spades. So there's 8 cards in the deck that are either an ace or a 2, and drawing any ace or 2 would be a successful result for this experiment. So I'm going to say the probability is 8 and 52. Really don't need the formula for that at all. And if I reduce 8 and 52 on my calculator, I do 8 divided by 52, math, enter, enter, I get that this fraction reduces to 2 over 13. If this was an odd problem, 2 over 13 would be the author's answer. 24 gets to be a nuisance, but I can get it without that formula pretty easy. What's the probability that I get a club or a red card? I know the denominator is going to be 52 because there's 52 cards in the deck. And now I can list the cards. There's going to be clubs. There's 13 clubs. The clubs go from the ace of clubs, 2 of clubs, 3 of clubs, all the way up to the jack of clubs, queen of clubs, king of clubs. There's 13 clubs that would be acceptable to pick, and any red card, which is any diamond or any heart. And there's 13 diamonds between the ace of diamonds and the king of diamonds, and there's 13 hearts between the ace of hearts and the king of hearts. The number of cards, if I listed all the cards that were acceptable, there'd be the 13 clubs that were the clubs, the 13 diamonds, and the 13 hearts, which were the red cards. So there'd be a total of 39 cards of the 52 cards that fit what I need them to fit. And so now if I go 39 divided by 52, math, enter, enter, I'm going to write 3/4 down. If I checked in the back of the book, if this was an odd problem, the author probably would just write the reduced fraction. 26 is going to be a nuisance. Cards, there's 52 different cards that you can pull from, and when the author starts wording problems like 26, I have to be ultra careful. 26 might be the only problem in this grouping that I might consider the formula for, but I think I can get the problem without the formula just as well. It'll be less confusing if I don't use the formula. So the first thing the author says is get a card greater than a 9, and our author considers an ace low. And then the author says, or any black card. The fraction is going to have a 52 in the denominator because I can get any one of 52 cards. When I'm listing all of the items, I just want to make sure not to double list. Black cards are easier for me. This is all the spades and all the clubs. There's 13 spades and 13 clubs. That's going to make up 26 cards. Now, in addition to those 26 cards, I want to write any card that's greater than a 9 that I haven't already counted. The cards that are greater than 9s are the 10s, the jacks, the queens, and kings of each of the 4 suits. So there's the 10 of diamonds, the jack of diamonds, the queen of diamonds, the king of diamonds, the 10 of hearts, the jack of hearts, the queen of hearts, the king of hearts, and then the 10 of spades, the jack of spades, the queen of spades, the king of spades, and then the 10 of clubs, the jack of clubs, the queen of clubs, and the king of clubs. So there's 1, 2, 3, 4. There's 16 cards that are greater than 9. If I did this, if I put in the numerator 26 plus 16, I put 42 in the numerator, that's not going to be the correct answer because I'm double counting. I've counted all the heart, spades, and clubs already. I can't count the spades and clubs when I'm counting cards greater than 9 because I've already counted them. I'm not allowed to double count. So when I'm counting the number of cards that are good, if I've already counted something in one category, I can't count it in the other category. So for the cards greater than 9, although there's 16 of them, 8 of them are already considered in the spades and the clubs. I'm just going to consider the 8 additional cards that I haven't already counted. So there's the 26 black cards and the rest of the cards that are greater than 9 that are red. And 26 and 8 is going to give me 34. So this fraction would be 34 over 52, and I'll reduce this. 34 divided by 52 equals, math, enter, enter, and I get 17 and 26. So the answer for 26 would be 17 and 26. So all of those problems, other than the formula problems, I could have done with the skills that I've already learned. These next problems, the problems between 27 and 34 on your homework, and the problems between 28 and 32 that I'm going to do, they can definitely be done with the skills that we have from the earlier sections, but it's going to be tedious. And the way that the author teaches to do the problems in this section is kind of a formula approach, and it's superior. So I'm going to do problems 28, 30, and 32 like I would do it if I didn't have any formula at my fingertips, and then I'm going to do the problems in a quicker way. And you'll appreciate the quicker way and probably not want to do the drawn out way. So 28, 30, 27 through 33, they all involve picking 2 cards from a special deck of cards. It's not your standard 52 card deck. These problems have birds and lions and frogs and monkeys. And as I read through the questions that the author is asking me, oh yeah, the author does get into some colors too. So what I'm doing here is I'm going to write down the sample space. If I can get a sample space written down then I can do well and answer any probability question that the author can throw at me. So there's two parts to the problems between 27 and 34. The author wants me to draw two cards, first with replacement, second without replacement, and the birds are the only ones that have special colors. So I have bird 1, bird 2, bird 3, bird 4, bird 5, and I'm going to color code them the best I can. The lions, the frogs, and the monkeys, I just want the numbers. So for my first card, I'm going to do sample space, and I'm going to do the smaller sample space. So I'm picking two cards. I'm going to do the drawing two cards without replacement. So the number of cards that I could get, there are there's 20 cards. So for my first card, there are 20 cards. Oh gosh, I can't do this. This is going to be insane. And then for the second card, there's going to be 19. 20 times 19. Oh, that would give me 380 elements in my sample space. I could list 380 elements in my sample space, but that's not going to be good for anybody. So let me back off the book for a little bit, make up a small problem that I could answer with a sample space and with the formula that the author introduces for me. So the problem with doing this problem like we've been doing, listing the entire sample space, is there's 380 elements in the sample space. It would take me an hour to write that down. That's not good. So I'm going to, before I just tell you the formula, create a problem that's not in the book and show you how you can get the problems solved using a formula. So I'm going to do a completely made up problem, and then I'll show you how to do it with a formula. So here's my cards. So my experiment, this is a completely made up problem to help you understand the formula that the author wants us to use for the problems that I just started to do but decided I just wasn't going to do. Okay, I'm going to say two cards are drawn, and let's do without replacement. Which makes it easier. Then I'll do one with replacement. From the following 5 cards. So my cards are going to have one card with the number. I'll do the 1 of hearts, the 2 of hearts, 3 of hearts, the 4 of hearts, or the 5 of hearts. So I'm taking from a deck of cards, I'm taking these 5 cards out, and I'm going to draw 2 of them without replacement. First of all, I'm going to say how many numbers will be in my sample space, like we've done in the last chapter. How many items, or in the last section, will be in my sample space. And I made this tolerable. I'm going to make 2 spots. There's a first card that I need to draw, and a second card. For the first card, I can draw any one of the 5 cards. When I say without replacement, once I draw that card, I'm going to not put it back. And when I go to draw my second card, there's only going to be 4 to choose from. So my sample space is going to have 20 different cards, or 20 different items in it. Now let me list the sample space, but I want to do it on another sheet of paper so that I can ask probability questions on that sheet and not run out of room. So I'm going to list the sample space. There's going to be 20 items, and I can do something like this. My first card could be the numbers 1, 2, 3, 4, or 5. I'm going to do this on the next sheet and then finish up the sample space. So my first card that I draw could be a 1 of hearts, could be a 2 of hearts, could be a 3 of hearts, could be a 4 of hearts, or could be a 5 of hearts. And our author would do this, although our author does the tree sideways. This is a fine way to do it. And then if my first card is the 1 of heart, my second card can't be the 1 of hearts again because I'm doing without replacement. So I could get the 2 of hearts, the 3 of hearts, the 4 of hearts, or the 5 of hearts. So the sample space for this would be a 1 of heart, comma 2 of heart, a 1 of heart first, and a 3 of heart second, and then a 1 of heart, 4 of heart, and then a 1 of heart, 5 of hearts. I really don't even need the hearts, but I have them, so I'm there. So I'm done with this. Now I'm going to go, if I get the 2 first, I could still get the 1, 2, 3, 4, or 5 of hearts. So the next part of my sample space would be getting a 2. I can't get a 1, a 2 should I say, because I'm not doing with replacement. So I could get the 2 of hearts with the 1 of heart, the 2 of hearts, not with the 2 of hearts, but with the 3 of hearts, the 2 of hearts with the 4 of hearts, and the 2 of hearts with the 5 of hearts. Now I'll go to the 3. With the 3, I could get the 1, 2, 4, or 5. Can't get the 3 because I'm doing without replacement. So I could get the 3 of hearts with the 1 of hearts, the 3 of hearts with the 2 of hearts, the 3 of hearts with the 4 of hearts, or the 3 of hearts with the 5 of hearts. And then I go to the 4. With the 4, I can get the 1, 2, 3, or 5. So I could get the 4 of hearts with the 1 of hearts, the 4 of hearts, then the 2 of hearts, the 4 of hearts, then the 3 of hearts, and then the 4 of hearts, then the 5 of hearts. And I do the same thing with the 5. If I get the 5, first I can get the 1, 2, 3, or 4. So I can get the 5 of hearts, then the 1 of hearts, the 5 of hearts, then the 2 of hearts, the 5 of hearts, then the 3 of hearts, and the 5 of hearts, then the 4 of hearts. If I can list a sample space, I can really do probabilities quickly. If I can't do the sample space, then I have to use a formula. So let me ask some questions that I could answer the probabilities for using the sample space. Then I'll show you how to do them and get in the formula. So my experiment was 2 cards are drawn from those cards from 1 through 5, and I did without replacement to make the sample space smaller. And let me try to do some probabilities that the author might want. How about this? How about the first shows, so what's the probability that the first is a 5 and the second is an even number? Okay, well I know the denominator is going to be 20 because there's 20 elements in my sample space. So the numerator is going to be anything that has the first number of 5 and the second number even. If I go through my sample space, that's this here and that there. Those 2 items in the sample space have the first number of 5 and the second number even, because 2 isn't even, 4 is even. So I say the probability is 2 in 20, and I'll reduce that to 1 in 10. So that's how I could get this answer doing a sample space. That's not going to be practical for the problem that I started doing, the problems between 27 and 34, because that sample space was going to have 380. So there's got to be a way to get 2 in 20 or 1 in 10 without listing the sample space, and it's not so hard actually. To do this probability, to get this answer of 1 in 10, I'm going to do the probability of each event separately and multiply them together. So to find this answer, which is the answer to this problem, I could list the sample space. There's 20 items in my sample space. Of the 20 items, 2 of them have a 5 first and an even second, so the probability is 2 in 20, which just reduces to 1 in 10. If I didn't have the sample space in front of me, I could still get the same answer. The probability of getting a 5 for my first. So for my first number, I could get any of the numbers between 1 and 5. The probability of getting a 5 on my first number, so my first number could be 1, 2, 3, 4, or 5. The probability that my first card is a 5. My first card, there are 5 different cards I can pick from, and one of them is a 5. Now, I took that 5 out. I'm not replacing it. What's the probability that my second card is even? Well, because I'm doing it without replacement, I assume that I got the 5, and I only have the numbers 1, 2, 3, and 4 left. What's the probability that my second card is even? Well, of the cards that are left, assuming I got the 5, there's 4 cards left because I started with 5, took 1 out, didn't put it back. And of those, there are how many evens? There are 2 evens. If I multiply these fractions, I multiply the numerators together. I go 1 times 2, and I multiply the denominators together, and I go 5 times 4. And in the numerator I get 2, the denominator I get 20, which is exactly what I got by listing the sample space. It's way more efficient to do this strategy to get your probability than it is listing a sample space, because listing a sample space of 20 was a nuisance, but it was doable. Listing a sample space of 380 is more of a nuisance, and this formula will get me to the answer every time. So let me try to do another one. How about this? What's the probability that the first shows a 4 and the second shows a 3? So now if I'm doing this formula-wise, or sample space-wise, I look through my entire sample space and I find every one that has a 4 first and a 3 second. The denominator is going to be 20 because there's 20 items in my sample space. And now I'm going to go through my sample space and find any one that has a 4 first and a 3 second. This one has a 4 first and a 3 second, and there isn't another one in the entire sample space that has specifically a 4 first and a 3 second. So this probability is going to be 1 in 20. Let me get the same answer using the formula without my sample space. So having the sample space, I know there's 20 items in the sample space. I search through the sample space, find the item that has the look that I want, that goes in the numerator, and I'm done. Formula, I do this. What's the probability that my first number is going to be a 4? Well, when I go to get my first number, there's 5 numbers to choose from, which were the numbers 1, 2, 3, 4, and 5, and only one of those is a 4. I'm going to cross it out and assume that I got it because I'm not doing replacement. Now I need my second number to show a 3. Well, my second number, when I go to pick it, the numbers that are left are 1, 2, 3, and 5 because I'm assuming I picked a 4 and I'm not replacing, so there's only going to be 4 numbers to choose from, and of those 4 numbers, there's only 1 3. If I do the multiplication that's implied here, the multiplication in the numerator is 1 times 1. The multiplication in the denominator is 5 times 4. This is going to give me the 1 over 20 that I got without using a formula. So the strategy for probability that the author wants us to do, if we're picking 2 cards from a deck of cards, or if we're spinning a spinner twice, which we're going to get to, this strategy of multiplying for probabilities is what the author wants us to do, because listing the sample space isn't really helpful or practical. So this is as a warm-up that gives us hopefully the idea of how I'm going to attack the problems that I started to attack and then I stopped. So for each of the problems between 27 and 34, the sample space is too large to compute probabilities, but I'm picking 2 cards. I'm going to do my probabilities just like this. I'm going to do the probability of getting the first card times the probability of getting the second card, and then multiply them together, and that would give me my probability without having to list the sample space, without having to know how big the sample space is. So this formula is, or this strategy of multiplying individual probabilities is a nice strategy, and it's useful, and it's used all the time. So now I'm going to get back to the book, and I'm going to do without replacement first, because we've been doing without replacement. So I'm going to handle problems 27 through 34. I'll do maybe both with and without replacement simultaneously. So 2 cards are drawn from this deck of cards. The author says once with replacement, so do one probability like I picked a card and then I put it back in, and then B, do my probability without replacement. I picked a card and I didn't put it back in. So I'm picking 2 cards. The sample space is impractical to write. Part 28 says, what's the probability that they both show the number 3? I'm going to do without replacement first because we've been doing without replacement. To do this, I'm going to multiply the probability of getting a 3 for my first card times the probability of getting a 3 for my second card. And these are both going to be fractions. So for the first one, if I'm just picking my first card, there are 1, 2, 3, 4 3s from the 20 cards. So the probability that my first card is a 3 is going to be 4 out of 20. Because in this deck of cards, there's 4 3s out of the 20 cards. So the probability that my first card is a 3 is 4 in 20. Without replacement says that 3, I'm going to pick it out, and then I'm going to pick another card. So what's going to happen is I'm going to take one of the 3s away, and then I'm going to pick a card from what's left. Well, what's left now isn't 20 cards anymore. There's only 19 cards. And regardless of the 3 that you got, once you pick a 3, there's 3 3s left. So my next fraction is going to only have 19 cards left because I started with 20 cards. I picked a card without replacement, so there's 1 card less left. So there's 19 cards for the denominator. I plucked a 3 out, so that means there's only 3 3s left. The next fraction, the probability of getting a 3 on my second, is going to be 3 in 19. Let me multiply these on my calculator. I'm going to go parentheses 4 divided by 20, parentheses, and then parentheses 3 divided by 19, parentheses, enter, math, enter, enter. My calculator tells me the answer to this should be 3 in 95. We go backwards and do this same problem but with replacement. The with replacement only affects the second fraction. It never affects the first fraction. So to do this probability, I want to find the probability of getting a 3 for my first card times the probability of getting a 3 for my second card. For the first card, the probability is still 4 in 20. There's 20 cards in the deck and there's 4 3s. The chances are 4 in 20. In the first instance, when I did without replacement, I didn't put my card back, so there were only 19 cards left to choose from. I took one of the 3s away, so there are only 3s left, 3 3s left. In this problem with replacement, my second probability is going to be the same as my first probability because I still have the same 20 cards to choose from. So it's going to be 4 and 20 again. And I'm going to multiply and simplify these quickly. So I'm going to go parentheses 4 divided by 20, parentheses 4 divided by 20, enter, math, enter, enter. My calculator tells me the answer for this should be 1 in 25. So I'm going to do 30 and 32. 30 wants the probability that the first is a 2 and the second is a 4. So I want the probability that the first is a 2 and the second is a 4. So I'm going to do this. I'm going to do it, first of all, I like doing without replacement. That's easier for me. And then I'll do with replacement. So I just need to do each probability next to each other. So I need the probability that the first is a 2, and then the probability, if I get that 2, that the second is a 4. The first probability is always going to have a denominator of 20 because there's 20 cards to choose from. And then I count all the 2s. There are 4 2s, a 2 with a bird, lion, frog, and monkey. So the numerator is going to be 4 out of 20 because 4 of the 20 cards are a 2. And then without replacement, I'm taking that 2 out. I'm left with 19 cards. Of the 19 cards, there's one of the 2's gone. I don't know which 2 is gone, but it doesn't matter. The numerator needs to be, of the 19 cards that are left after I pull out a 2, how many are 4s? And there's 4 4s. So this is going to be 4 and 20 times 4 and 19, and I'll reduce this on my calculator. So 4 divided by 20, parentheses, 4 divided by 19, parentheses, enter, math, enter, enter, and I get 495. So that's without replacement. Without replacement, this denominator always increments down. If I do this with replacement, the denominator is going to be 20 for both of them. So I'm going to do the probability that the first is a 2. That's still the same. There's 4 2s, 4 cards with 2 of them of the 20 cards. And then for my second card to be a 4, if I put that 2 back in, there's going to be 20 cards left to choose from, and of those 20 cards, 4 of them are still 4s. And when I do this probability, 4 divided by 20, parentheses, parentheses, 4 divided by 20 equals, math, enter, enter, I get 1 in 25. And now the last one I'll do is the first is a lion, the second is a red bird. Oops, I'm sorry, I should do that first. They both show even numbers, I'm sorry. I skipped. So 32 is they both show even numbers. So I'll do without replacement first. Just for me, that's easier. I might as well get the one I know I can get right. So I need the first to show an even number, and then the second to show an even number. The probability that the first shows an even number, I need to count through the cards. There's 4 2s and 4 4s, so all of the 4 2s and the 4 4s, there's 8 cards of the 20 that show an even number. I'm going to pull one of those 8 cards out. I'm going to be left with 19 cards, and I have to get another even. I started with 8 even, but on the first one I took one of the evens away, so I only have 7 left. So my second fraction is going to be 7 and 19. Without replacement, I don't put the card back, so there's only 19 cards to choose from for my second. And now a cheat, 8 divided by 20, parentheses, 7 divided by 19, parentheses, enter, math, enter, enter, and I get 14 and 95. And then part C, with replacement, I need the first to be even, and of the 20 cards, there's 4 2s and 4 4s that are even, and then I'm going to replace, and for my second to be even, it's still going to be 8 out of 20 because I'm putting the card back that I took. There's 20 cards, there's still going to be 8 evens. And so if I do 8 divided by 20, parentheses, 8 divided by 20, enter, math, enter, enter, I get 4 and 25. I hadn't planned to do 34, so I'm going to skip it. But if you get stuck on the homework because 34 somehow was going to be magical to help you understand the problem, then we'll have plenty of time in class for you to ask me how to do that. So the next group of problems we're going to work with are spinner problems, 41 through kind of 48 are all spinner problems. And spinner problems can be done just the same way as card problems. They could have their probabilities found by multiplying. So if I look at problem 40, and I want to compare it to a card problem, spinner problems are kind of like card problems with replacement. So the problem 40 is like a card problem with replacement. So what's going to happen in problem 40 is I'm going to spin this spinner twice. It wants the probability on my first spin getting a red and then the second spin getting a yellow. And to do that, I'm going to multiply the probability of getting a red on the first. So I'm going to do red first times yellow second, and multiply the results together. Just like getting one card then another card, I can find the probabilities by multiplying the probability of each event happening. The probability of getting a red on this spinner for number 40 is 1 in 2. And then regardless of what happened on the first spin, the second spin, it could happen, the chances of getting red again are 1 in 2, the chances of getting yellow again are 1 in 2. What happens on the first spin doesn't impact the probability on my second spin, so I can't increment the denominator down. Each spin is independent of each other, and on every spin the probability of getting a red is 1 in 2, the probability of getting a yellow is 1 in 2 regardless of the spin. If I multiply these fractions together, I'll get the probability is 1 in 4 to get a red than a yellow. If I went down to do 42, that's a new spinner. Didn't say I was going to do it, but I'll do it. 42, I need to make the parts equal. They're not equal parts, so I made it into 4 parts, having 2 greens and 1 red and 1 yellow part. So when you're doing spinner problems, you have to make each of the pieces the same size. And now this wants me to spin the spinner twice and get a red on both. To do that, I do the probability of getting a red on the first spin. There's 4 regions that are equal side. There's one of them that's red, so the probability of getting a red on the first spin is 1 in 4. The probability of getting a red on the second spin is still that same 1 in 4. If I multiply these together, I get the probability of getting a red on both spins is 1 in 16. If I'm doing 44, I need to make this pie have 8 pieces. So to make the pieces equal, I split the red and I split the yellow and made equal pieces. So 44 wants to get a color other than yellow on both spins. On the first spin, the probability of getting a color other than yellow, there's 1, 2, 3, 4, 5 regions that aren't yellow. So the probability on the first spin of getting a number other than yellow, a color other than yellow, is 5 in 8. So this is for problem 44. And on the second spin, I still have that same probability of 5 and 8 getting a color other than yellow. On spinner problems, my probabilities never change. The probability in every spin is the same. So I'm going to multiply 5 times 5 and get 25, 8 times 8 and get 64, and that fraction doesn't reduce. Problems 45 through 48 are referring to the spinner that I looked at in problem 42. And when I do problem 46, I'm not sure how well you can read this, hopefully you have your book. It wants a red on the first spin and a yellow on the second spin. Spinning twice, the probability of getting a red on the first spin, I made it 4 regions. So for problem 46, the probability of getting a red on the first spin is 1 in 4. The probability of getting a yellow on the second spin is 1 in 4. If I multiply those, I get 1 in 16. For 46, the probability of getting a red on the first spin and a yellow on the second spin. 48 wants me to get a yellow on the first spin and a color other than yellow on the third spin. So for 48, I'm looking at this picture right here. the probability of getting a yellow on the first spin, there's one yellow region out of the 4 equal side regions. And then I'm going to multiply by getting a color other than yellow on the second spin. That would be getting red or green. There's 2 greens and 1 red region, so there's 3 of the 4 regions that are other than yellow. If I multiply these, 1 times 3 is 3, 4 times 4 is 16. The probability is 3 in 16. The next problems, the author gets into children problems. And when I'm working with children problems, it's a lot easier for me to do the problems with the sample space. It's definitely possible to do the children problems with the formula, but it's just harder. And so rather than fitting these problems into this section, it's practical to do the children problems without using the formulas, and I just don't like the formulas for this, so I'm going to do the children problems 49 through 52, and make it old school. I'll show you the formula approach, and if you decide you like the formula approach better, then that's fantastic. So I'm going to write a sample space for the couple having 3 children. Notice that the probability of having a boy is 50%, or 1 in 2, which means the probability of girl is 1 in 2. That's important. This using the formula approach that the author's using assumes that every event has a 50-50 chance or equal chance of happening. And then this word independence I haven't talked about. This allows you to multiply to do probabilities, but I don't want to get that's overly technical. So let me handle 50 without the formula and using sample spaces, and then with the formulas, and you can decide how you want to do it. So for 49 through 52, the couple is going to have 3 children. And I'm going to list down a string of boys and girls. There's going to be 8 elements. My first child could be a boy or a girl. My second child, depending on what the first child is, still could be a boy or a girl. And my third child can be a boy or a girl, regardless of what the first 2 children are. The sample space for this, hopefully you do these quickly now. I could have a boy first, a boy second, and a boy third. That's getting to that boy. A boy first, a boy second, and a girl third. That's getting to that G. A boy first, a girl second, and a boy third. That's getting to that B. A boy first, a girl second, and a girl third. That's getting to that G. And then I'll do these. A girl first, a boy second, and a boy third. A girl first, a boy second, and a girl third. And then a girl, and a boy, a girl, and a girl. So those are the 8 things in the sample space. When sample spaces are small, using the formula really isn't saving me that much. But when the sample spaces are big, that multiplication style helps a lot. So first 50 says, what's the probability that all 3 are girls? There's 8 items in the sample space, so my denominator has to be 8. The numerator is the number of things in the sample space that are all girls. It's going to be 1 in 8. To do the formula approach to get this 1 in 8, the probability that my first child is a girl, we'll say it's a 50-50 chance, 1 in 2. The probability that the second child is a girl, the independence means the probability of a girl is 1 in 2 every time. If it wasn't independent, then the probability of getting a girl might be higher or lower if you had a girl for your first kid. But that's not something that we're going to horribly worry about. So the probability of getting a girl on the first time is 1 in 2. The probability of getting a girl on the second is 1 in 2. The probability of getting a girl on the third is 1 in 2. If I multiply the numerators together and multiply the denominators together, in the numerator, 1 times 1 times 1 is 1. In the denominator, 2 times 2 times 2 is 8. So I could have not listed the sample space and got the probability of 1 in 8 by just multiply the probability of each of the individual events. Girl first, girl second, girl third, 1 in 2 times 1 in 2 times 1 in 2. That will take me there perfectly. So 52 wants me to do the youngest is a girl, and then it wants the middle to be a boy, and then it wants the oldest to be a girl, if I look for mine goes old, so I want the oldest to be a girl, so it's in this column. The middle to be a boy, so it's either this one right here or this one right there, and then the youngest to be a girl. For my sample space, this is the one that fits that. It has the oldest a girl, the middle a boy, the youngest a girl, and there's only one element in my sample space of the 8 that has that look. To do this, without the sample space, the probability that the youngest is a girl is 1 in 2. The probability that the middle is a boy is 1 in 2, because the middle is a 50-50 chance it's a boy or a girl. The probability that the oldest is a girl is 1 in 2. And if I do that same multiplication, 1 times 1 times 1 over 2 times 2 times 2, I get the 1 in 8 that the author's looking for. The last group of problems I can only do by the formulas, and they just don't seem to fit as nicely. For me, they don't feel as nice. But I'm going to do these problems the same way. So far we've kind of done something like everything that you'll be exposed to up through 53. We have 2 banks of problems to look at. The problems between 64, that should say 66, and then 68 and 70. And each one of these are probability questions that I can only answer using the multiplication strategy. So I'll do the probability of the first event times the probability of the second event times the probability if there's a third event to get the probability of what's going on here. So when I look through the next bank of problems I'm going to look at, 63 through 66, we have 30 women who had their home built, and 19 of them would recommend their builder. So 19 of the 30 would recommend their builder. 6 of the 30 said, no, I won't recommend my builder, and 5 out of the 30 aren't sure. 3 women are selected. What's the probability that whatever would happen? To do any of these probabilities, I'm going to multiply 3 probabilities together. The probability of the first woman doing something, the probability of the second woman, and then the probability of the third woman. So when I go to answer probabilities for 63, 64, 65, and 66, I'm picking 3 women. Each of the answers I'm going to get by multiplying 3 probabilities, the probability that the first woman would do what they say the first woman has to do, times the probability the second woman would do what she'd have to do, times the probability the third woman would do. So I need to know some probabilities. The probability that a woman would recommend her builder is 19 out of 30. The probability that a woman would not recommend her builder is 6 out of 30. And the probability that the woman is not sure is 5 out of 30. So if I do 64, the probability the first would not recommend, the second and the third would recommend. I'm going to form 3 fractions. I'm going to write first recommend times second not recommend times third recommend. Make each a fraction and multiply them together. So when I do problem 64, it's a multiplication, and I multiply each of the individual probabilities together to get my answer. So real specifically, I need to know, the probability in general that somebody would say yes or recommend is going to be 19 and 30. The probability that they'd say no or not recommend is 6 and 30. So this is recommend, won't recommend, and not sure. The probability that somebody that's surveyed is not sure is going to be 5 and 30. So problem 64, so what's the probability that the first would not recommend, the second and the third would recommend? So yes, they'd recommend, and yes, they'd recommend. To do the answer to this question, I'm just going to find each probability and multiply them together. And I have to be careful here, because in this particular problem, I'm picking from these group of 30, and the first one, if she didn't recommend, the probability is 6 and 30. So there's a 6 and 30 chance that I pick a woman that didn't recommend. I'm picking just from this group of 30 women. I'm done with the first woman. I can't pick her again. I'm only going to have 29 to choose from my second. And how many are left that said yes? So I picked one of these that said no. So there's only 5 left that said no. But I'm looking for one of the 29 that are left that said yes. There's 19 that said yes. So the probability of getting from the remaining 29 people one that says yes is 19 of 29. Now I'm going to scrub out that person. There's only 18 now that would say yes, 5 that would say no, and 5 that are not sure from the 28 that are remaining. So now there's 28 women remaining, and of those 28, 18 would say yes. So to do this probability, this is kind of like a without replacement because there's only 30 women that I'm picking from, and once I pick one of the 30 women, I'm done. I can't pick them again. So I'm going to multiply these fractions together and reduce. So clear parentheses 6 divided by 30 parentheses 19 divided by 29 parentheses 18 divided by 28 parentheses math, enter, enter. I'm going to get 171 over 2030, and I'm not going to reduce that. Let me peek in the back of the book to see what kind of answers the author's giving for the problems 63 and 65 in section 12.6, just to make sure that the author didn't sneak a decimal in at me. That's possible. That's not that pleasant of a fraction. So 12.6, for 63, the author did a fraction. Let me do 63 to get that 969 over 4060 just so you can see it. So I'm shooting for 969 over 4060. So what is 63? Oh, 63 would be they all recommend their home builder. So if I come backwards and do 63, it's they all would recommend. So the first would say, yes, I recommend it. The second would say, yes, I recommend my builder. And the third would say, yes, I recommend my builder. Well, in general, there's 30 people. There's 19 of them that would say yes. Once I pick from one of those 30, there's only going to be 29 left. I've taken one of the 19 that would say left. Yes, there's only 18 left. And for the third person, once I've pulled 2 of the 30 away, I only have 28 left. And there's going to be 17 left that would say yes. Let me multiply these fractions together. Go 19 divided by 30 parentheses, 18 divided by 29 parentheses, 17 divided by 28, enter, math, enter, enter, and I get 969 over 4060, just like the author wanted me to get. So for each of the problems in this bank of problems between 63 and 66, it's kind of like doing a card without replacement, because once I've taken one of the women and plucked them in, I only have the 29 left, and once I've done 2, I only have 28 left. Okay, last problem I want to do is 67 through 70, and this bugs me a little bit, I think, because it doesn't increment down like this one does. So it doesn't look like it. By just glancing at it, it feels like it's a without replacement. This is supposed to be more like a with replacement problem. And at this point, these problems don't look that different. Why would this one be a without replacement and this one be a with replacement? And that gets a little subtler than I care to get. So let me do the problem how the author wants, and maybe I'll come up with something that is profound to help you differentiate between the problems. So the big difference between the home builder problem and the drug problem is, in the home builder problem, 30 people had their homes built. I was surveying those 30 people. If I read through this problem right here, 100 different patients were given a drug. 70 reacted favorably, 10 reacted unfavorably, and 20 were unaffected. If I was randomly picking from those 100 people that were actually given the drug, then I would increment down. It'd be like a without replacement. But this isn't this case. I'm giving the drug to 3 people, Mr. Rivera, Mrs. Rivera, and their son Carlos. And those 3 people, Mr. and Mr. Rivera and their son Carlos, aren't one of the 100 people that were already given the drug. So when I do the probabilities, the probability is not going to increment down. I'm not going to go 1 over 100, 1 over 99, 1 over 98. This is because in this problem, the people that were given the drug weren't one of the test patients. Whereas in problems 63 through 66, the people that were surveyed were people that were of these 30. So that's why I did the first problem, 63 and 64, by incrementing down, but I'm not going to when I do 69 and 70. So when I read through the problems for problems 67 through 70, we have 100 people that were given a experimental drug. 70 out of the 100 had a favorable reaction. And 10 of the 100 had an unfavorable reaction. And 20 of the 100 were unaffected. If my probability question says, what is the probability that I take 1 or 3 of these actual 100 people that were given the drug, and what's the probability that 1 was favorable, 1 was unfavorable, and 1 was unaffected, then I'd increment 100, 99, and 98. But because the Carloses weren't part of this experiment, they're not actually part of these 100, then each one of them has, we'll say, each one of the Carloses has a 70% chance of reacting favorably, 10% chance of acting unfavorably, and 20% chance of being unaffected. And the fact that one of the family members is favorable doesn't impact the chances of the others being favorable. That's the word independence in the problem. The word independence kind of tells me not to increment down. So if 67 through 70, the people that were being tested were part of the probability questions that increment down. But these are people that are new people that haven't been given the drug yet. So there's going to be 3 people, Mr. Rivera, Mrs. Rivera, and Carlos that are given the drug. And then what's the probability that Mrs. Rivera, so I'll just do all of these, what's the probability that Mrs. Rivera, only Mrs. Rivera reacts favorably? Well, her chances of reacting favorably, we'll say, is just like the general population, at 70 and 100. There's no multiplication doing there because I'm only looking for one person's probability. If I need to have the probability for 2 people or 3 people and getting their reactions before I can do multiplication. 68 is both Mr. and Mrs. react favorably, and then Carlos is unaffected. The probability that Mr. Rivera reacts favorably is 70 and 100. If this was a test question and an in-class test question and you showed your work and you incremented down, I wouldn't take points off. So if your next fraction was 69 over 99, I'm not going to be that picky. If I see that, I'm not going to take points off. But because Mrs. Rivera wasn't part of these 100, her chance is just as the same as her husband's. It's still 70 and 100. And Carlos's chance of being unaffected is still 20 and 100. If you would have written 70 times 100, 69 times 99, 20 times 98, I'd live with that. I can completely see why you might want to do it that way. It's not supposed to be done that way, but I can definitely live with that. So let me try to do this on my calculator. my calculator tells me the chances of these three events happening is 49 in 500. The difference between 67 and 68 is 67, I'm only asked about one person, so I don't need to multiply probabilities. 68, I'm asking about three people. I need to multiply each of the probabilities. I didn't increment down because Mr. and Mrs. Rivera and Carlos, they're not part of these 100 people. They're just, what if they gave the drug to them? Whereas in the home building problem, these were actually picking people that had their homes built. And the last one, 70, is none reacts favorably. So I'll do Mr. is not, it's either unfavorable or unaffected. Mrs. isn't favorable, so she's unfavorable or unaffected. And Carlos is not favorable, so he's unfavorable or unaffected. So to not react favorably, you're in one of these categories. So the probability that Mr. Rivera doesn't react favorably is the opposite of the 70 of 100, which is 30 over 100. It's either the 10% chance that he's unfavorable or 20% chance that he's unaffected. And similarly, Mrs. Rivera is going to have the same 30% chance, and Carlos is going to have the same 30% chance. So if I do these, 30 divided by 100, parentheses, 30 divided by 100, parentheses, 30 divided by 100, parentheses, enter, math, enter, enter, I get 27 in 1,000. Again, if your work, and you wrote 30 times 100, 29 times 99, 29 over 99, 28 over 98, you showed that on the test. I'm not going to take points off, but because the Riveras weren't actually given the drug, it's not proper to increment down. So that's everything that I needed to do in section 12.6. 12.6 is definitely a step up harder than 12s 1, 2, 3, and 5, but it's still going to be in the in-class portion of the test. Hopefully later on this weekend I shoot the video for the review, and if you look at the review, you'll be able to understand exactly what you're responsible for from the first 6 sections, but we skipped section 4, so really the first 5 sections, 12s 1, 2, 3, 5, and 6. And then once you perfect that, then it's kind of all downhill, because what's going to be left we're going to do as a take-home test. And as doing a take-home test, you in some sense have unlimited time to do the test, so you could really pour through the material and make sure you understand it. So just once you get the first part of chapter 12 perfected, then you're going to be ready to do the test, and everything else should be kind of stress-free.